99 minutes. One of the planet's top physicists takes you racing through aliens, UFO files, string theory, the Big Bang, black holes. Whether we're living inside a simulation, consciousness, artificial intelligence, quantum computers cracking every code on Earth in a second, and immortality. His name is Michio Kaku, one of the founders of string theory and one of the best science communicators alive. He recently went on the hit podcast, The Diary of a CEO, and left behind a string of jaw-dropping one-liners. The clips are everywhere. In this video, we're not here to debunk him and not to worship him. We're going to do something more useful. Take an honest ruler and sort every big claim into where it actually belongs. Because the problem usually isn't that he's wrong, it's that he quietly slides between three very different kinds of statement without telling you. So we'll use just 4 labels. Tier 1, confirmed, textbook grade, solid science. Tier 2, frontier, serious research, but not yet settled by experiment. Tier 3, his own speculation, bold guesses that are Kaku's, not the consensus of physics. And Tier 4, overstated. The core may hold, but it's been pushed too far. Let me put the verdict up front so you don't mistake the spirit of this video. Kaku is strongest when he explains established physics, curved spacetime, black holes, the scale of the universe, the limits of our senses, and makes it give you goosebumps. He's easiest to misread when he phrases his own speculation in the voice of what we think. This isn't a list of flaws. It's a user's manual. Learn it, and the next time a sensational science headline grabs you, you'll be able to weigh it yourself. Which tier is this? Let's start on his home turf, the equation that's supposed to explain everything. Kaku says the string theory he spent his life on is the theory that eluded Einstein, a theory of everything, an equation compact enough to fit the universe's forces onto a single page. In his telling, the fundamental particles are nothing but tiny strings, vibrating in different ways, different vibrations, different particles. First, why we'd even want such a thing? Physics today rests on 2 pillars that don't get along. One is the standard model, which describes every known particle and 3 of the 4 forces with staggering precision, but leaves out gravity. The other is general relativity, which describes gravity perfectly, but isn't a quantum theory. At the center of a black hole, at the instant of the Big Bang, both languages break down at once. A theory of everything would stitch them into one. String theory is one of the most mathematically developed attempts at that stitching. It has a beautiful quirk. For the equations to be consistent, spacetime can't have just the 4 dimensions we know. It needs 10 or 11, with the extra ones curled up too small to see. Particles or vibrations of strings is an accurate description inside string theory. I'll give that a frontier. Why not confirmed? Because to this day, there is no prediction that only string theory makes, and that has been verified. To probe the scale of a string directly would take energies far beyond any conceivable collider. It's an extraordinarily elegant, powerful mathematical candidate, but the experimental bridge to the real world still isn't built. In 2026, Caltech made headlines. From a few basic assumptions, researchers derived string-like structures and showed how string theory tames the infinities of quantum gravity. It sounds like string theory wins, but notice the wording of the report itself. It stresses that this is not experimental evidence, and that a real, direct test still needs energies out of reach. So when Kaku says, "We're very close," I have to label that line overstated. The field has made major mathematical progress. That's true, but close to the final equation is a feeling, not a timeline. String theory has been neither falsified nor confirmed. It hangs in the most fascinating and most difficult place. Following string theory, Kaku floats a particularly romantic idea. The dark matter wrapped around the Milky Way might be a higher octave of string vibration. Matter that, because it's tuned too high, doesn't interact with light, so we can't see it. Let's nail down the solid part first. Dark matter itself is confirmed, at least its gravitational effects are. Galaxy rotation curves, the motion of galaxy clusters, gravitational lensing, bending light, the pattern of the cosmic microwave background, the growth of cosmic structure. 5 independent lines of evidence all point to a great deal of unseen mass out there. It is not an illusion, but what dark matter actually is, we don't know. In the 2024 review by the Particle Data Group, a long list of candidates, weakly interacting massive particles, axions, warm dark matter, primordial black holes, self-interacting dark matter, are all still on the table, none confirmed. Decades of expensive detectors deep underground have yet to make a single definitive catch. In the higher octave of a string theory really can give rise to dark matter candidates, like axion-like particles or Kaluza-Klein modes. But dark matter is the next octave of the string, is Kaku-style poetry, not what the field has measured. So this line gets his own speculation. Here's a line worth taking with you. Dark matter is a real mystery. Kaku's octave of a string is one possible poetry for that mystery, not its measured solution. Telling a possible poetry apart from a measured solution, that's the very muscle this ruler is meant to train. Now the most gripping part. Kaku runs a quick calculation. The Milky Way has about 100 billion stars. Suppose 10% have Earth-like planets. Then he says the odds of life are almost 100%. The first half of that math is rock solid. NASA estimates that roughly half of Sun-like stars may host a rocky planet in the habitable zone, able to hold liquid water, conservatively about 50%, optimistically as high as 75%. So planets are common, and habitable rocky planets are common too. That stands. Confirmed. But the second half, leaping from planets to life, is almost 100%, skips the single biggest unknown in all of science. How, and how hard, does chemistry become life? That process is called abiogenesis, the origin of life. And about how often it happens, we know almost nothing. Why nothing? Because we have exactly one data point: Earth. Bayesian studies repeatedly show that a single sample can't pin down the probability. It could be high or low enough to span hundreds of orders of magnitude. Some researchers even argue that once you honestly fold in the uncertainty of every term in the Drake equation, there's a substantial chance intelligent life is rare. That's the famous Fermi paradox and the great filter. So life is almost 100%, I label overstated. Note, this is not saying alien life doesn't exist. It very likely does. It's saying that until the probability of life's origin and the bottlenecks along the way are far better constrained, we have no right to call it almost certain. This is one of the best corrective hooks in the whole episode, worth remembering for life. Planets are common. Life is not yet statistically solved. Keep the wonder, but common planets does not equal common life. The episode's headline is all about "they're lying to you about UFOs." But here's the twist. On this topic, Kaku is actually one of the most level-headed voices. He says the vast majority of sightings can be explained. Only a small remainder is unresolved. The files released in 2026 contained no compelling hardware, and a lot of the footage is two-dimensional, so distance and scale are genuinely hard to judge. On the timing, he's right on the money. The US government's Pursue archive really was declassified in waves through 2026. A first tranche on May 8th, a second on May 22nd, a third on June 12th. The release of these files genuinely happened. Confirmed. But between unresolved and alien lies an entire galaxy. AARO, the office that investigates this, put it bluntly in its 2024 historical review. It found no verifiable evidence that any sighting represented alien activity, no evidence that the government or private industry possessed alien technology, and no sign that anyone illegally withheld information from Congress. So a small fraction might be visitation stays at frontier, unproven. Here's a line worth pinning next to every bombshell. Unresolved does not equal alien, but unresolved does not equal alien, but unresolved does not equal fake either. Admitting we don't yet know is itself a kind of scientific honesty. On this thread, Kaku brings up a famous star, one whose brightness inexplicably drops by about 20%, and muses about whether it could be a giant energy-harvesting alien structure, the legendary Dyson Sphere. This is Tabby's star. An alien megastructure was indeed its most viral early explanation, but later multi-wavelength observations badly weakened it. NASA's Jet Propulsion Laboratory concluded that the long-period dimming most likely comes from an uneven cloud of dust, because the infrared and ultraviolet dim by different amounts, whereas a solid, opaque megastructure should block all wavelengths roughly equally. So Tabby's star is an alien structure, gets overstated, outdated. But Tabby's star isn't a gotcha story. It's a model of how science self-corrects. The weird signal was real. Better data simply replaced the explanation. The most fascinating thing about science was never always being right. It's being able to get it right. Since aliens can't easily fly here, Kaku also does the math on us flying there. With a chemical rocket like the Saturn V, reaching the nearest star would take about 70,000 years. That math is basically right, confirmed at the speed of today's probes. Getting to a neighbor a few light years away really is a tens of thousands of years affair. So he brings out the science fiction favorite, the warp drive. Not making the ship go faster through space, but bending space itself, compressing it in front, stretching it behind, carrying the ship along inside a bubble of space-time. In theory, he says, it's possible. It just needs an enormous amount of energy. That's true, but the "in theory" deserves heavy emphasis. The Alcubierre metric and later warp metrics really do show that the equations of general relativity allow such exotic spacetime geometries. But the classic models require negative energy, an exotic matter that violates the energy conditions. And even the newer positive energy or sublight versions are nowhere near engineering. So warp drive is frontier. The line to remember here: in this domain, theoretically possible means we can write down a self-consistent spacetime geometry, not we know how to build the machine. General relativity hands science fiction a language. It hasn't yet handed engineering a device. The conversation turns to the beginning of the universe. Kaku says the Big Bang created our expanding universe. But what triggered the Big Bang? He offers two romantic guesses. String theory can describe a bounce rather than a one-off bang, and our universe may be just one bubble in an enormous bubble bath of universes. First, nail down what's solid, that the universe is expanding and began about 13.8 billion years ago from a hot, dense state. That's confirmed. The cosmic microwave background, the abundance of the elements, the recession of galaxies all cross-confirm it, and the Planck satellite's parameters are still the benchmark of the standard model. On what happened after the Big Bang, physics stands on very firm ground. But what came before, and what triggered it? That's unsettled. A bounce? Loop quantum cosmology, cyclic models, eternal inflation, a multiverse from the string landscape. These are all serious research programs, but not one has evidence anywhere near as strong as the evidence for expansion in the microwave background. So bounce and bubble bath are frontier. Kaku's image of frothing bubbles actually blends two different things: the quantum vacuum fluctuations that genuinely exist in quantum field theory and pure speculation about cosmic origins. Vacuum fluctuations are real, but one vacuum bubble became our universe is a hypothesis, not an observed event. A useful distinction: physics is very strong on what happened after that hot, dense state, and much weaker on why there was such a state at all. Now black holes, the most reliable stretch of the whole episode. That gravity is curved spacetime, that black holes exist, event horizons, escape velocity, all mainstream physics. The compact object at the center of the Milky Way, Sagittarius A star, is strongly supported by decades of stellar orbit observations and by Event Horizon Telescope imaging. The 2020 Nobel Prize in Physics went exactly to the theory of black hole formation and the discovery of that supermassive object at the galactic center. In 2022, we even took its picture. This whole stretch is confirmed. But then Kaku says the inside of a black hole might be a door to another universe, something like a wormhole. In general relativity, wormholes really are valid solutions under special assumptions, but a traversable wormhole generally needs exotic matter or violations of the energy conditions, and there is zero evidence that a real astrophysical black hole is a door. So a black hole is a door gets his own speculation, imagination at the edge of the equations. The basics are rock solid. That door should be clearly stamped imagination. The host throws out that late-night soul question: could we be living inside a supercomputer simulation? Kaku's answer is probably not. But his reason is a bit shaky. He says simulation theory conflicts with quantum theory because quantum theory is probabilistic. First, the idea itself. Philosopher Nick Bostrom's original simulation argument is not a proof that we live in a simulation. It's a trilemma. Either civilizations almost never reach a post-human stage able to run such simulations, or post-human civilizations almost never bother running ancestor simulations. Or the vast majority of minds like ours are in fact simulated. It forces a choice among three. It doesn't hand you an answer. Kaku's conclusion, probably not, is reasonable in itself. There's genuinely no good evidence we're in a simulation. But his specific reason is weak. A simulated universe could perfectly well contain random processes, pseudo-random numbers. And if it runs on quantum hardware, even true quantum randomness. Quantum being probabilistic does not refute the simulation idea. So I label this reasonable conclusion, weak argument. So what's the genuinely strong objection? Computing cost. Simulating an entire universe down to the quantum level is astronomically expensive, and unfalsifiability. It makes no unique, testable prediction. The clean way to put it, the simulation hypothesis isn't defeated by quantum randomness. It's weakened by its unfalsifiability and its astronomical computing assumptions. This next stretch is the best science communication in the whole episode. Kaku says human perception is only a tiny, survival-tuned fragment of the real world. Ultraviolet, infrared, X-rays, radio, cosmic rays. To almost all of it, we are blind. That part is confirmed. NASA puts it plainly. The electromagnetic spectrum stretches from long radio waves all the way to gamma rays, and the human eye sees only a vanishingly narrow band of it, visible light. The colorful world in front of you is really a thin slit on a vast spectrum. The evolutionary layer holds up too. Organisms never perceive the world as it is. They perceive only the part their senses evolved to detect. Bees see ultraviolet, pit vipers see infrared, and we're locked into visible light. Kaku's word illusion is rhetorically strong, but more precisely, our perception isn't false, it's partial and biologically filtered, confirmed in popularized language. Why do I love this stretch? Because it turns physics into humility. Reality is not limited to what your nervous system reports to you. That's the best thing science communication can do. Not make you feel you know everything, but make you realize how little of it you actually see. From perception, Kaku turns to consciousness. He says consciousness is awareness, the source of meaning, and that the frontal brain is a time machine obsessed with simulating the future. That future-facing cognition is genuinely well supported. Psychologists call it prospection and treat the linking of remembered pasts with simulated futures as a core feature of human thought. Confirmed on that point. But he overdraws it in two places. First, consciousness is future simulation is a framework of Kaku's, not a settled theory of consciousness. Consciousness remains one of science's hardest unsolved problems. Second, he stretches the human-animal contrast too far. Crows cache food for later, great apes prepare tools for future use. Planning for the future is not a human monopoly. So this stretch gets his own speculation, a fascinating framework, not settled neuroscience. On artificial intelligence, Kaku's tone suddenly turns conservative. He says today's AI is essentially insect-level intelligence. It only imitates and recombines, with no real originality, and certainly can't produce new physics. At best, it might help us reshuffle laws we already know. This is the most dated stretch of the whole episode. In 2024, the Nobel Prize in Chemistry went to AlphaFold, which predicted the structures of nearly all of the roughly 200 million known proteins, used by more than 2 million researchers across 190 countries. That's not recombining. That's genuinely moving a whole science forward. In 2025, Google DeepMind unveiled AlphaEvolve, an evolutionary coding agent driven by a large model, which discovered and optimized algorithms, including faster matrix multiplication, and solved math problems with automated evaluators, finding better solutions humans hadn't known. So, AI only imitates and can't discover gets overstated. But let's be honest in both directions. Kaku is half right. Today's AI is genuinely not an autonomous general scientist. It can make discoveries inside narrow spaces with clear evaluators, but it still leans heavily on humans to frame the problem, supply the data, build the tools, verify the results, and interpret the meaning. So the balanced line is frontier. AI has already made real scientific contributions in constrained domains. Whether it can originate and validate deep theory across domains on its own is still open. On one other AI topic, though, Kaku is describing something happening right now: AI weapons. He mentions the fiber optic guided drones on the Russia-Ukraine battlefield. That one is confirmed. Fiber optic drones are exactly a key battlefield adaptation. Controlled by a physical cable, they bypass radio jamming. And reports note that autonomous navigation with machine vision can sharply raise strike success rates under heavy electronic warfare. This is the most concrete, least science fiction face of AI risk. The most comment section igniting stretch is this one. Kaku says quantum computers compute on atoms, have infinitely many states between 0 and 1, and could crack any digital code, banks, even Bitcoin. The host adds, Google's timeline is 2029. Quantum computers are real, but there are two things to correct here. First, the description of a bit is too loose. A quantum bit is a complex amplitude superposition, and the moment you measure it, you still get a classical 0 or 1. Its power comes from interference, entanglement, and algorithms, not from storing infinitely many states. Infinite states between 0 and 1, so it can do anything, is a popular myth, overstated. Second, and more important, the scope of crack any code is wildly exaggerated. What's genuinely threatened is public key cryptography, the kind based on factoring and discrete logarithms, like RSA, elliptic curves, Diffie-Hellman. The thing that does it is the famous Shor's algorithm. But symmetric encryption, the AES used everywhere in your bank and your phone, and hash functions are affected very differently. Quantum gives only a square root speedup, which you offset by doubling the key length. In other words, AES itself stays secure. As for 2029, that is not a date when Q-Day definitely arrives. It's a timeline Google set for migrating to post-quantum cryptography. What it stresses is the harvest now, decrypt later risk, and moving signatures and authentication to quantum-resistant algorithms as soon as possible. The U.S. National Institute of Standards and Technology already formally approved post-quantum standards in 2024. So 2029 equals the bank's collapse overnight gets overstated. Bitcoin is the same. Its real exposure is mainly not the SHA-256 hash, but public key signatures, especially old-style addresses whose public keys are already exposed. And even then, dealing with it is a matter of governance and protocol upgrades, not press one key and the bank goes to 0. The most precise line? Q-Day is not the day all encryption dies. It's the day unmigrated public key systems stop being safe. The biggest temptation, planted in the very first minute of the podcast, is immortality. Kaku says telomeres are like a biological clock. Telomerase can stop that clock. And since cancer also uses telomerase, an indefinitely extended lifespan might be tantalizingly close. The underlying biology is real, confirmed. Telomeres are protective caps on the ends of chromosomes. Every time a cell divides, they usually get a little shorter. Telomerase can rebuild them. The discoverers of this mechanism won the 2009 Nobel Prize, and many cancer cells gain their unlimited proliferation precisely by reactivating telomerase, or some other telomere maintenance trick. But aging is not one clock. The modern hallmarks of aging framework lists a dozen interwoven mechanisms: genome instability, telomere attrition, epigenetic changes, loss of protein balance, failing autophagy, deregulated nutrient sensing, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, altered cell-to-cell signaling, chronic inflammation, microbiome imbalance. Telomeres are just one lever in that web, and a dangerous lever. Because if you casually switch telomerase back on without also keeping tumor suppression in check, what you're doing is exactly what cancer does. So immortality is tantalizingly close gets overstated. The one-line summary: Telomerase may reset one aging-related counter. Cancer is precisely what happens when cells ignore too many counters at once. Near the end, the conversation turns to human nature. Kaku says religion functions as social glue, that Genesis is metaphor, not literal cosmology, that morality is shaped by lived experience, and that warfare has been part of human evolution. Yet our brains let us make moral choices beyond the struggle to survive. Religion as social glue is frontier, not just Kaku's notion, but a serious hypothesis in cognitive science. Norenzayan and colleagues' Big Gods theory proposes that prosocial religious beliefs and rituals may have helped expanding societies sustain large-scale cooperation. But the literature is far more nuanced than religion-created morality. Those same researchers explicitly note that religion is not a necessary condition for cooperation or moral behavior. Markets, kinship, law, secular governance sustain cooperation too. So this is best understood as a theory of religion's function, not a verdict on whether religion is true. As for humanity is on a knife's edge, that designer germs, nuclear weapons, runaway AI could destroy us, while progress could bring the moon and Mars, cures for cancer, and abundance. Those risk categories are frontier, mainstream topics in the study of existential risk. His phrasing is dramatic, but the core is right. Modern science hands civilization, at once, unprecedented control and an unprecedented capacity for self-harm. It's just that those specific predictions about the year 2100 are, to be honest, reasonable visions, not evidence-backed forecasts. And curing cancer is something of a category error. Cancer isn't one disease, it's hundreds. Kaku's best high-level theme isn't really doom, it's agency. The same technological civilization creates both the hazard and the tools to diffuse it. All right, 99 minutes, and we've walked the whole thing. Looking back through this ruler, Kaku is strongest where he makes established physics thrilling. Curved space-time, black holes, the scale of the universe, the limits of our senses, the real cryptographic threat from quantum computing. He's easiest to misread where he phrases personal speculation as what we think, the octave of a string, the alien megastructure, the robotic UFOs, the black hole door, immortality just around the corner. So what this episode really leaves you with isn't don't believe him. It's a skill. Rigor is never about dissolving the mystery. It's about labeling the mystery correctly. Next time a science headline sets your pulse racing, run it through 4 words first. Confirmed? Frontier? Speculation? Or overstated? The moment you can ask that question, you've already gone further than the clickbait. I'm your old friend. See you next time.